Okay. Everything that we're doing today is about unit conversion. The problems all boil down to doing unit conversions. We're going to work with motion that is circular. One thing that we want to do that we've already done before is perform rate conversions related to circular motion. We've done that before. It's just been so long that we're going to do an example here and then use it some more. And then we're going to solve some applied problems involving circular motion. That's our goal. Here's an example. We've done this type of problem before. But let's take a minute and review how to do it. Suppose you have an object rotating so that it turns 38.7 radians every second. We want to know how many revolutions per minute that is. We set up the conversion as a unit rate. So we would take 38.7, our units of our units of radians on the top, and our unit of time on the bottom. Now we want to set up a unit conversion that's ultimately going to get us into RPM, which is revolutions per minute. So we need to get rid of radians and go to revolutions on the top. What's the conversion between radians and revolutions? That's right. This fact you need to recall, 2 pi radians is always equal to 1 revolution is equal to how many degrees? 360. Basic three-way conversion fact that we'll be using frequently here in the next half an hour or so. So we can get rid of radians. We know that there are 2 pi radians in 1 revolution. Now if we were to quit our conversion there, what would the units on our answer be? Revolutions per second. We don't want revolutions per second, we want revolutions per minute. So we got to get rid of seconds and go to minutes. There are 60 seconds in a minute. Now we have revolutions per minute. That's what we want. Now if you convert that, multiply it out, you will end up with, we can keep 3 sig digs. These are exact conversions. We can keep all 3 sig digs and we get 370. Put a line above that 0 to show that that unit is significant. It's not really wrong if it's not there, but good practice. And the units are RPM. We're done. So let's turn about 370 times per minute. Grant. All right, well, we'll be doing more angular velocity. This is referred to as an angular velocity. If you're going down the road, your velocity or your speed could be in miles per hour. Or if you're running, it could be meters per second or feet per second. When something's turning, we measure how many degrees or radians or revolutions it's turning in a unit time, and we have what's called angular velocity. And that's basically the bread and butter of what we're going to work with here. Angular velocity is the rate at which something turns. Your speedometer tells you the rate that your car is moving, but angular velocity, and the symbol for angular velocity is the symbol omega, which looks awfully similar to a W, but no straight lines in there. And that's a pretty widely accepted symbol for angular velocity, so we'll stick with that. Just like the speed of your car is given by distance divided by time, our angular velocity, we don't know how far something is moving. All we know is how many degrees, radians, or revolutions it's turning. So it's going to be some angle divided by time, where theta is always going to give us our angle measure, as it always has, and t is a symbol for time. And the most common one that you are familiar with is revolutions per minute. That's an example of angular velocity. It's the rate at which something is turning. Revolutions per minute. Theta will always have units of degrees, revolutions, or radians. Got to be one of those 3. Time is typically going to be in seconds, minutes, or hours. So that means the units on omega have to be some combination of that. It could be degrees per second, or it could be revolutions per hour, or it could be radians per minute, or it could be revolutions per second. But it's going to be some combination of those two, or those choices. Okay, well, let's do a couple of examples involving angular momentum, angular velocity. Questions about the general idea? No? Here's what we've got. Let's give you a pleasant picture to daydream about. Merry-go-round is turning along 22 times. It turns during a 4-minute ride. We want to know what the angular velocity is in radians per second and what the... Well, let's just find out what the angular velocity is first. We'll put it in the desired units later. But our angle measure is 22.0 what? Revolutions. Here, since we're dealing with a large, usually revolutions are used when something's turning more than a complete revolution. 22 revolutions per 4.00 minutes, which means we can find out what the RPM of that merry-go-round is, and it turns out to be 5.50 revolutions per minute, or RPM, you could write. Okay, so we found its angular velocity. Now we want it in radians per second and degrees per second. So we just need to do the conversion. 5.50 revolutions per minute times, let's get rid of revolutions. Let's do radians first. 2 pi radians. And then we want it in radians per second instead of radians per minute. So we'll get rid of that minute and go into seconds. That gets us in radians per second. That works out to 0.576 radians per second. And we're done with the first question. There it is. Notice that we know nothing about the size of the merry-go-round. Doesn't matter. All that matters is that's how many degrees it's turning. Doesn't matter whether it's those little merry-go-rounds that they used to have outside of Kmart for a quarter, or, well, anyway, let's answer the second part of the question. I don't know what happened there. Yeah. Okay, well, let's just let's go one more step here, and let's go into degrees per second. So I'm going to go back. We wouldn't have to, but I'm going to go back and use the 5.50 revolutions per minute. That worked out exactly. Okay, this we had to round off, so we'll go back to the value that we had exactly. Except instead of getting rid of revolutions and going to radians now, we're going to go to degrees. And if you crank that out, you'll find out that this thing is turning at a rate of 33 degrees per second. Leading up to that, let's suppose we've got an aircraft prop and it turns at 4,300 RPM. We want to know how many degrees it turns every millisecond. Well, what are we looking for? Are we looking for an angular velocity, an angle, or a time here? We're looking for a time. We know that omega is equal to theta over t. We know what our angular velocity is. That's given to us as 4,300 RPM. We also know what time period we're interested in. That is 1 millisecond. We want to know how many degrees that turns. So, well, a millisecond isn't very long. So here's what we've got. First of all, rearrange your equation. If omega is theta over t and we're trying to solve for theta, multiply both sides by t, and it must be true that theta is omega times t. So then we know that our angle, how many degrees does it turn? That's going to be omega, which we know to be 4,300 revolutions per minute, times t, which is 1 millisecond, or 0.001 seconds. We can put a 1 underneath there. That's our time. But the problem is what? If we just multiply those two together, units are a mess. We got to make the units jive. First of all, seconds and minutes don't cancel. So put a conversion factor in there that'll make them cancel. Let's put seconds down here and minutes up there. 1 minute is 60 seconds. Now, the time all cancels and we're left with revolutions. That's all fine and good, but we don't want the answer in revolutions. We want it in degrees, so we have to do one more. 1 revolution, 360 degrees. Now revolutions cancels. We've got an angle in degrees. Everything cancels out. As long as you're using the relationship between omega, theta, and t correctly, the units will always work out just the way you want them. And if you solve that, theta turns out to be, what does theta turn out to be? There it is. Just about 26 degrees. So that propeller is moving fast, but a millisecond is so slow that it's not moving very far. Okay. The last topic is linear speed. If we know, think about this example for a minute. If we know how fast something is turning and we know the size of the circle that it's turning in, we can figure out what its linear speed is. Here's an example. Somewhere is an example. Here's an example. Suppose, just think about this very simple case to try and put this in perspective. Suppose we've got a perfectly round lake that has a diameter of 6 miles, or in other words, a radius of 3 miles. You are going to go for a leisurely walk around this lake. Now, I'm not going to tell you how fast you walk. I'm just going to tell you your angular velocity around this lake. You start walking around the lake at a rate of 1 radian per hour. So you're going to walk at 1 radian per hour, which means how many degrees roughly around the lake are you going to get? You remember a radian is equal to roughly how many degrees? No? 1 radian? It's going to be a radius stretched around here, somewhere up about there. About 57. Not good enough to use as a conversion, but an intuitive kind of a feel for how big a radian is, about 57 degrees. So if you walk at 1 radian per hour, you're going to get 57 degrees around the lake each hour. But that also tells you how fast you're moving, because how far is 1 radian going to be if you're walking around the edge? It's 3 miles. Okay? So if you take your angular velocity and multiply it by the radius, this becomes 1 radian per hour. Your velocity will be 1 radian per hour times 3 miles per radian. Your radius is 3 miles per radian, or in other words, 3 miles. But the units cancel off and we're left with 3 miles per hour. It's the same thing. So we can turn an angular velocity into a linear velocity by taking the angular velocity and multiplying it by the radius. Let's do an example. The key to note here, though, is if we're going to find a velocity from an angular velocity, omega has to be in radians. Otherwise, the units won't cancel. So omega's got to be in radians. So let's go back to our merry-go-round for a minute. We already figured out that this merry-go-round is turning at 0.576 radians per second. Okay, we figured that out about 2 slides ago. That's how fast the merry-go-round is turning, which is around 33 degrees per second. Now, we're going to assume that little Sally is sitting on this horse, which is 9 feet 6 inches, or in other words, 9.5 feet from the center of the merry-go-round, which makes that, and it's 9.5 feet exactly, so we'll put some extra sig digs on there. So how fast is she moving? Well, our velocity is equal to our linear velocity is equal to our angular velocity times the radius. We just need to make the units work. So her velocity will be 0.576 radians per second times the radius of 9 feet. Now, how do you make your units cancel when you do that? It's 9.5 feet. That is your radius, but we could also say that that's 9. She's traveling 9.5 feet per radian that she moves. So every time she turns a radian, she moves a radius distance. 9.5 feet per. That was weird. It's going to be quiet now? I don't know what that's all about. Well, the simple solution is to turn it off. Hope it doesn't do it again. It was relaxing, though, for a minute, though, wasn't it? Okay, so now the units cancel. Her radius is 9.5 feet per radius, or per radian. Those cancel, and her velocity turns out to be 5.47. The units have got to be feet per second. We could convert that into miles per hour, but it's so slow that we'll just leave it in feet per second. 5.47 feet per second. We're done. All right. Idea, the connection between linear velocity, angular velocity, all depends on the size of the circle that you're traveling in. Let's do another one. Drive home today. Average car tire is about 27, 28 inches tall, 26 to 28. So how fast are they turning when you're going 55 miles per hour? Well, the key is that when your tires turn, they have to turn so that the tread of the tire is moving your car at 55 miles per hour. Now, what are we looking for here? Are we looking for angular velocity, r, or linear velocity? We know the linear velocity. The edge of that tire has to be being turned at 55 miles per hour. We want to find the angular velocity because the question says how many RPM. That tells you what is your angular velocity. So if we want to find angular velocity, we can rearrange that. Our angular velocity is going to be given by v over r. So v over r, that's the same as, for the sake of setting it up like a unit conversion, that's the same as saying v times 1 over r. Okay? That'll allow us to set it up like a conversion like the other ones that we've done. You can set all these problems up as conversions if you just make sure that your units cancel out correctly. So we have our velocity, which is 55.0 miles per hour times 1 over the radius. Now, what is 1 over your radius going to be? What is your radius? 13.5 inches. What units have to go up here? Something has to go up there. That's 1 what? 13.5 inches is your radius, or in other words, it's a radian. Okay, a radian and a radius are always the same length. That's what changes this distance into an angle. That's what's changing your distance into an angle. So instead of a linear velocity, it becomes an angular velocity. Now we just need to make our units line up. We want what? We want revolutions on the top and minutes on the bottom. Suggestions? We want to get RPM, so revolutions per minute. Let's get rads into revolutions. 2 pi radians is 1 revolution. So that cancels off the radians. Yeah, we've got miles and inches, 2 units of distance here that somehow need to cancel. Right now they're not. So let's get something to cancel there. We can get rid of the inches. 1 foot is 12 inches. Now we need to make feet and miles go away. One mile is 5,280 feet. Yeah, if we were to stop here, we'd have revolutions per hour. That's not quite right. Okay, so we have one more step. We're going to multiply that by let's see here, 1 hour. How many seconds in an hour? 3,600. 60 seconds in a minute, 60 minutes in an hour? Oh, I'm sorry. Yeah. So never mind. 1 hour into 60 minutes. I'm glad you caught that. 60 minutes. So we can cancel off hours. Now what units are we left with? We're left on the top. All we've got left is revolutions. On the bottom, minutes. That's what we want. So again, once you follow your basic formula, omega is V times 1 over R. It's just a matter of getting your units to cancel the way they have to, and it'll come out in the wash. So our angular momentum, or excuse me, our angular velocity works out to be 685 RPM, 685 revolutions per minute.